This video will demonstrate how to do a hypothesis test for one proportion. When hypothesis testing, we want to use the standard error, and as you recall, the formula for standard error has P in it. P is the unknown parameter value. So in a practical situation, like when we're doing a hypothesis test, we don't actually know what P is. That's one of the reasons why we're doing the test. So what are we going to do in this situation? Well, when we're doing a hypothesis test, we're always assuming that the null hypothesis is true. If the null hypothesis is true, that means that P is equal to the value under the null hypothesis, which we call P naught. So we can use P naught to substitute in our standard error equation, so we can be able to calculate the standard error to do hypothesis tests. That makes our resulting test statistic look like this. We're going to have z equal to p hat minus p naught divided by the standard error with p naught substituted in. So square root of p naught times 1 minus p naught over n. The requirements for this are that n times p naught and n times 1 minus p naught are both greater than or equal to 10. This is a little bit different than the requirements for a confidence interval, in which we require the successes and failures to both be greater than 10. In this case, n times p naught and n times 1 minus p naught are not actual count values from our data. They are quantities that will have to be calculated to see if we meet the requirements. So let's look at an example. Of the 2,430 Major League Baseball games played in 2009, the home team won in 54.9% of the games. If we consider 2009 as a representative sample of all Major League Baseball games, is this evidence of a home field advantage in Major League Baseball? The first thing we need to do is define our parameter. Since we're doing a problem dealing with one proportion, then our parameter is P, the population proportion, and P is equal to the proportion of all Major League Baseball games that would be won by the home team. Next, we're going to state our hypotheses. The hypotheses are always written in terms of the population parameter, which in this case is P. In our case, we're wanting to know if there's a home field advantage. So there would be a home field advantage if you were more likely to win on the home field. So in other words, if you won on the home field more than half the time. That makes our null hypothesis P equal to 0.5, and then the alternative hypothesis P greater than 0.5. Remember, the equal sign always goes in the null hypothesis, and the alternative hypothesis goes right along with whatever our research question is. Next, we're going to find our sample statistic. In this case, the sample statistic is going to be the sample proportion, or in other words, the proportion in our sample of games that were won by the home team. It tells us in the problem that the home team won in 54.9% of the games. That makes our sample proportion 0.549, and the correct notation for that is p hat. Next, we're going to check our requirements. Remember, the requirements for a hypothesis test are different than the requirements for a confidence interval. In a hypothesis test, we want n times p naught and n times 1 minus p naught to both be bigger than 10. So n is our sample size. In this case, it's the 2,430 games. So we take 2,430 times p naught. P naught, remember, is the value claimed under the null hypothesis, which in this case is 0.5. So if we take 2,430 times 0.5, we get 1,215, which is certainly larger than 10. We do the same thing for the other quantity. We're going to take n times 1 minus p naught. In this case, that's 2,430 times 1 minus 0.5, which ends up being the same thing of 1,215, which is still bigger than 10, so we do meet the requirements for the normal approximation. Now we're ready to go ahead and actually start doing the test. The next thing we want to do is find our test statistic. So here is our formula for the test statistic, and we can take all the values that we know and plug those in order to calculate the value of our test statistic. So once I plugged everything in and worked it all out, I end up with z equal to 4.831. Just a couple things to point out in this formula here. The denominator portion of our formula is what we call the standard error. And the end result here, this 4.831, is going to be our test statistic. Now we use the test statistic to help us find the p-value, and we do that using the normal distribution. Because p hat follows approximately a normal distribution, we can use areas under the normal distribution curve to help us figure out the p-value. So to do that, I'm going to go into StatKey. In StatKey, I'm going to go where it says theoretical distributions, and I'm going to choose normal. The default that comes up is the standard normal distribution, and that's the one that we want to use to be able to plug in our test statistic. So in our case, we were looking for greater than in the alternative hypothesis. That's a one-tailed test to the right. So I'm going to click on right tail. Then down here in this little box, I'm going to enter in the value of my test statistic, which in this case was 4.831. When I do that, then the value up here in the floating box is my p-value. Notice that my value was so small that StatKey started using scientific notation to record it. So it says 6.8 e negative 7. So my p-value is 6.8 times 10 to the negative 7th, and that would translate to being 0.0000068. Obviously that's super duper duper small, and it's okay if you want to go ahead and round that to 0. P-value of essentially 0 is obviously really, really, really low, and when p is low, HO must go. So for our conclusion, we would reject the null hypothesis. We have strong evidence that the proportion of games won by the home team is greater than 50%. Let's look at another example. Does the order in which wine is presented make a difference? Subjects were asked to taste 2 wine samples in sequence. Both samples given to a subject were the same wine, although subjects were expecting to taste 2 different samples of a particular variety. Of the 32 subjects in the study, 22 selected the wine presented first when presented with 2 identical wine samples. Do the data give good evidence that subjects are not equally likely to choose either of the wines? All right, so first step is to define our parameter. In this case, P would be the proportion of people who would choose the first presented wine. Next, we're going to write our hypotheses. If they were equally likely to choose the first presented or the second presented wine, then the probability that they would choose the first one would be 50%. So under our null hypothesis, again, if we're saying that there's no difference in the probability of choosing either wine, it'd be 50-50. So our null hypothesis would be p equals 2.5. For our alternative hypothesis, if you recall our research question, it says, do the data give good evidence that the subjects are not equally likely to choose either of the wines? So that's indicative of a two-sided test, not equals, to put in our alternative hypothesis. So the alternative hypothesis, p not equal to 0.5. Next, we're going to compute our sample statistic, p hat. To compute the sample statistic, we take the number of people in our sample who chose the first wine divided by the total number of people in our sample. That's 22 over 32, or 0.6875. Next, we're going to check the requirements. The requirements for a hypothesis test are that n times p naught and n times 1 minus p naught are both bigger than 10. In this case, that would be 32 times 0.5. Remember, the value that we use here is the value under the null hypothesis rather than the p hat value like we use when we do a confidence interval. 32 times 0.5 is 16, which is greater than 10, so we're good there. And then we do the same thing for n times 1 minus p naught. That actually ends up being the same answer of 16, which is also bigger than 10. So we do meet the requirements, and we can continue with our hypothesis test. The next step is to compute the test statistic. We plug in all the values that we know, and we solve for the test statistic. So this formula is not quite as nasty as the ones that are in section 6.3, and you will be required to use this formula on exams in order to calculate test statistic. Once I put in all the numbers, I end up with a test statistic of 2.121. From here, I use that test statistic to help me find the p-value. So I'm going to head back over to StatKey. In StatKey, I'm going to choose the normal theoretical distribution, And this was a two-sided test, so I can click on two-tailed. My test statistic was 2.121. That's positive, so I'm going to enter that on the right box down here. So I enter 2.121 and hit return, and this gives me a picture of what the areas are that I'm looking for. The area in each tail is 0.017. Now because this is a two-sided, or in other words a two-tailed test, then I have to add the area in both tails together. So that 0.017 plus the 0.017 on the other side. When I do that, I get a p-value of 0.034. Now all I have to do is state my conclusion. 0.034 is low, and when p is low, HO must go. So we're going to reject the null hypothesis. We do have sufficient evidence that the proportion of people who choose the first presented wine is greater than 0.50. Or in other words, the order of the presentation does seem to matter.